Measurement of voltage, phase and frequency by C.R.O. Okay. Measurement of voltage, phase and frequency by C.R.O. In laboratory, C.R.O. is frequently used to measure voltage, amplitude, phase and frequency of an unknown source. Okay. In laboratory, C.R.O. is frequently used to measure voltage, phase and frequency of an unknown source. Okay. First, measurement of voltage. Measurement of voltage. Okay. When the X1, X2 plates, X1, X2 plates of C.R.O. are earthed, its time-based circuit switched off. And no voltage applied to the YY and no voltage applied to the Y1, Y2 plates. Okay, we get a sharp, bright spot of light at O on the screen. Okay, if a DC voltage is now applied by connecting Y2 to the positive and Y1 to the negative. Okay, if the DC voltage is connected to the positive Y2 and negative Y1 to the negative Y1 of the DC source, the spot of light is displayed towards the positive plates Y2, and separate at O dash. Okay, instead of O, and separate at O dash instead of O, separate of O dash instead of O. The displacement of the spark O dash, the displacement of a spark O dash. Okay. If the spark of light is displaced towards the positive plate Y2 and appears at O dash instead of O, the displacement of the spark O dash is directly proportional to the applied voltage. Okay. And when an AC voltage is applied to YY plates of the C.R.O. and keeping XX plates earthed, the spark keeps on moving up and down to variation of potential or voltage. Okay. When an AC DC voltage is crushed and applied to AC voltage. When an AC voltage is applied to the plates Y1, Y2 of the C.R.O. keeping X1 and X2 are earthed, the spark keeps on moving up and down. Due to variation of potential or voltage, but due to persistence of vision, a line is traced on the screen. The length of the line corresponds to peak value of an AC voltage and thus gives 2 under root 2 RMS voltage. Okay. RMS voltage. If V is the deflection sensitivity of the C.R.O. and if V is the deflection sensitivity of C.R.O. voltage required to produce a unit of deflection of 1 mm, and the displacement of the spark in the first case are the length of line, in second case is what Lmm. Then unknown voltage, unknown voltage capital V equal to V multiply L. This should be noted that DC voltage measurement, the calibration is also done with DC, and for AC voltage measurement the calibration is done with AC. Okay, this should be noted that this should be noted that the for DC voltage measurement, okay. This should be noted that for DC voltage measurement, the calibration is also done with DC, okay, and for AC and for AC voltage and for AC voltage measurement, the calibration is done with AC. Second point. Measurement of phase difference. Measurement of phase difference. Okay. Measurement of phase difference. Okay. Lisa-Joule figures found on a cathode ray tube oscilloscope screen can be used to measure the phase difference between two sinusoidal voltages of the same amplitude and frequency. Okay? Lisa-Joule figure found on a cathode ray oscilloscope when measurement of phase difference. Okay, Lisa-Joule figures found on a cathode ray oscilloscope. Screen can be used to measure. Screen can be used to measure the phase difference between two sinusoidal voltages of the same amplitude and frequency of the same amplitude same amplitude of the same amplitude and frequency, okay, same amplitude and frequency, the two signals applied simultaneously to the horizontal and vertical deflection plates x1 and x2 and y1 y2, okay, the two signals are applied simultaneously to the horizontal and vertical deflection plates x1, x2 and y1, y2 if the two voltages are present as x equal to a sine omega t. Okay, this is the equation number first, and y equal to a sine omega t plus phi. This is the equation number second. Okay, where phi is the phase angle by which the sinusoidal voltage y leads the voltage x, where phi is the phase angle, phi is the phase angle by which the sinusoidal voltage y leads the voltage x, okay. Equation number second can be put in the form y from the equation number second y equal to a sine omega t cos phi plus a cos omega t sine phi, okay. Now x square equal to a square sine square omega t equal to a square 1 minus cos square omega t, okay. Then a square cos square omega t equal to x equal to a square minus x square, then a cos omega t equal to under root of a square minus x square, okay, x square, and this is the equation number third, okay. Substituting equation number third, we have substituting equation number third, we have y equal to x cos phi plus under root of a square minus x square sine phi, okay, and y minus x cos phi whole square equal to a square minus x square sine square phi, okay, or y square plus x square cos square phi minus 2xy cos phi equal to a square sine square phi minus x square sine square phi, okay. Then y square plus x square minus 2xy cos phi equal to a square sine square phi. A square sin square phi. This is the equation number 4. Okay. This is the equation number 4. Okay. This is the equation number 4. According to equation number 4, the Lissajous figure is an ellipse. The Lissajous figure is an ellipse. According to equation number 4, according to equation number 4, the maximum displacement A, capital A, and the vertical displacement y naught. Maximum displacement capital A and vertical displacement y naught time t0 can be measured from the vertical scale of the C.R.O. Okay. Put in t equal to 0 in equation. Second, we have y naught equal to a sin phi. Okay. This is y. X. This is y naught a. Okay. Y naught a. Then sin phi equal to y naught by a. Okay. Our phase difference phi equal to sin inverse y naught by a. Thus, the phase difference phi can be calculated by the measurement value of a and y naught on the elliptic trace found on the C.R.O. screen. Okay. Thus the phase phi can be calculated by measuring the value of capital A and y naught on the elliptic trace formed on the C.R.O. screen. Okay. Thus, the phase phi can be calculated by measuring the value of a and y naught on the elliptic trace found on the C.R.O. screen. Okay. Third point, measurement of frequency. Measurement of frequency. Okay. The frequency of Gibbs source can be measured by comparing the frequency of the source with that of a standard oscillator. This is done by obtaining Lissajous figures on the C.R.O. screen by connecting the standard frequency oscillator to the vertical deflection plates Y1, Y2, and unknown frequency source to the horizontal deflection plates X1, X2. It is assumed that both the oscillator execute simple harmonic motion. Okay, the frequency of the gives source, the frequency of a given source the frequency of a given source can be measured by comparing the frequency of the source comparing the frequency of the source with that of a standard oscillator with that of a standard oscillator. This is done by obtaining Lissajous figures on the C.R.O. Screen by connecting the standard frequency oscillator to the vertical deflection plates Y1, Y2, and the unknown frequency source to the horizontal deflection plates X1, X2. It is assumed that both the oscillators execute simple harmonic motion. Okay. Since simple harmonic motion plotted against the time gives sinusoidal configuration, two sinusoidal electrical inputs to a cathode ray oscilloscope will give Lissajous pattern on the screen. The exact pattern traced out, the nature of the resultant path depends upon the frequency or period, amplitude and phase relationship of the two inputs. Okay. First, equal frequencies are periods. 1 minute. Equal frequencies are period. Later, the two simple harmonic vibrations having the same period take place along the x and y axis respectively. This can be represented as let the two simple harmonic vibrations let the two simple harmonic vibration having the same period take place, having the same period take place, having the same period take place along x and y axis, respectively. This can be represented as x equal to a sin omega t and y equal to b sin omega t plus phi, where a and b are the respective amplitude and the y vibration is ahead of the x vibration by electron phase angle. Okay. Then if where a and b represent respective amplitudes, and y vibration is ahead of the x vibration by phase angle phi, if phi equal to 0, then x equal to a sin omega t, okay, and y equal to b sin omega t, okay. Then y equal to b by a into x, okay. This represents a straight line through the origin as shown in the figure. You can show a light figure. This is 0 and this is x-axis. This distance is a and this distance is b, and this show angle theta. This show angle theta. Okay, this is the first figure. Okay, then this represent a straight line through the origin. Okay, and tan theta equal to b by a. Okay, tan theta equal to b by a. If phi equal to pi by 2, then x equal to a sin omega t and y equal to b sin omega t plus pi by 2, that is b cos omega t. Then this is the x square upon a square plus y square upon b square equal to 1. This represents a symmetrical ellipse. Figure. How? Ellipse, okay? This is B, this is A, pi by 2, okay? Pi by 2, okay? X square upon A square plus Y square upon B square equal to 1. This represents a symmetrical ellipse whose major and minor axis coincides with x and y axis respectively. Okay. If third point, this is first point, this is a second point, and a third point. If A equal to B, the resultant curve is a circle given by x square plus y square equal to A square. Okay, equal to A square. Okay, and the resultant curve is circle. The resultant curve is circle. Okay. The resultant curve is circle. Okay. Circle. And if fourth point, if phi equal to pi, then x equal to a sin omega t and y equal to b sin omega t plus pi, that is minus b sin omega t, then y equal to minus b by a into x. Okay, the figure is pi b a angle theta. Okay, this again represent a straight line through the origin as shown the figure. The slope is given by tan theta equal to minus b by a. Okay, tan theta equal to minus b by a. For phi equal to pi by 4 and phi equal to 3 pi by 4, for phi equal to pi by 4 and phi equal to pi by 4 and phi equal to 3 pi by 4, we get oblique ellipses as shown the figure. You can show the figure. First figure is as like this. 1 minute. 1 minute. This is pi by 4 and a b, and second figure is opposite, just opposite. Just opposite. Okay, 3 pi by 4. Okay, just opposite. 3 pi by 4. Okay. Then pi by 4 and pi equal to 3 pi by 4, we get oblique ellipse as shown in the figure, and as phi exceeds pi, the whole cycle is repeated in the reverse order. Okay. Okay. If a pi exceeds pi, the whole figure is repeated in the reverse order. Reverse order. This is important. The whole figure. Okay. Okay. If pi exceeds pi, the whole figure repeated reverse order. Okay. Okay. Next, frequency in the ratio of 1:2. Frequency in the ratio of 1:2. 1 minute. 1 minute. 1 minute. 2.2. Frequencies in the ratio of frequencies in the ratio of 1:2. Frequency in the ratio of 1:2. Frequencies in the ratio of 1:2. Okay. When the frequency of the Y vibration is double that of the X vibration, but the two are in phase phi equal to 0, the curve traced out in shown in the figure. You can show the figure. 1 minute. When the frequency of the Y vibration is double. When the frequency of Y vibration is double. When the frequency of the Y vibration, when the frequency of the Y vibration is double, Y vibration is double that of the X vibration, that of the X vibration, but the two are in phase, phi equal to 0. The curve traced out is the curve traced out is figure. Traced out this figure. This figure, okay? If however the frequency of the X vibration is double that of Y vibration, if however the frequency of the X vibration, the frequency of the X vibration, the frequency of the X vibration is double that of Y vibration, then the pattern, then the pattern, then the pattern obtained, then the pattern obtained is, you can show the figure, you can show the figure, and like this, okay? In fact, the frequency ratio of the two inputs may be determined from an analysis of the Lissajous figure produced. A simple method is to enclose the Lissajous figure in rectangles whose sides are parallel to the formation axis of the figures. Note that the number of tangency points along the vertical and the horizontal axis, the ratio of the number of tangency points is in the inverse ratio of the two frequencies. Okay, inverse ratio of the two frequencies. Okay, number of tangency points along the x-axis. Then, according to Lissajous figure, number of tangency points, along x-axis upon number of tangency points along y-axis equal to frequency of y vibration, frequency of y vibration, frequency of y vibration upon frequency of x vibration, frequency of x vibration, okay, frequency of x vibration, okay. Then this figure is, according to this figure, y frequency upon x frequency equal to 2, and according to this figure, y frequency upon x frequency equal to 1 by 2. Okay, the cases of y frequency upon x frequency, you can show this figure. In this figure, and the first figure, this is second figure, this is third figure, and 1 minute. This fourth figure is as like this. Sorry, I like this. Okay? Okay? This fourth figure, and the ratio of the cases of the cases of y frequency upon x frequency equal to 1:1 in the first figure and 2:1 in the second figure and 1 and 1:2 in the third figure, 1:2 in the third figure, and 3:2 in the fourth figure. Okay, as the standard frequency oscillator is connected to the YY plates, the frequency of Y vibration is known, hence the frequency of X vibration is that of the unknown frequency source can be calculated. Okay, next heading linear acceleration.